and welcome all. And I really want to thank Jennifer for navigating through this very complex WebEx confusion. I can tell you that I was underwater while she was navigating and clicking. So thank you all. Thank you especially, Jennifer, for managing it. So again, thanks to the automotive division. This is the second opportunity I've had to speak to you folks. Last time was in June of last year, where I have a little talk on hypothesis testing. Our agenda today is to have a short introduction of a DOE, and it is such a wide subject. Again, this is just a very, very kind of skimming the surface kind of discussion today. We'll talk about how DOEs work and some basic terminology. I'll give you a couple of examples, a one-way and a two-way ANOVA, and then lead into the Taguchi fractional factorial designs, the L4 and the L8. So we'll start out with statistical experiments. As you know, they allow us to determine if an experimental change has been made on a process results in a change on the product, and which process inputs then have control over a given process output, and how much each process input contributes towards a given result. Statistical experiments allow us to know how a process works instead of thinking we know how a process works. It's very common on the manufacturing floor when there's a lot of question about a process. There's a lot of people with facts, and you really can't, opinions, and you really need to have that replaced with facts. So maybe this has been your problem. It certainly has been mine over the years. You're responsible for a manufacturing process that's not operating properly. You're getting lots of help from material suppliers, operators, the quality team, engineering and maintenance. And guess what? There's no agreement on a solution. There are so many process inputs, and you're not sure which ones to change and which ones to just leave alone. Your boss is quite excited due to the high scrap and poor yield, and you need some help to know how to proceed. Well, DOE, or design experiments and hypothesis testing, are statistical methods which improve the efficiency and reliability of process improvement and problem solving. And to that, they're fast, good, and cheap. While other methods are available, none compare to these two statistical tools for arriving at the right answer in the least amount of time and at the lowest cost. A designed experiment is a planned information gathering exercise where variation is present. It's planned. And the intent of the experiment is to evaluate the effect of changing the level of specifically selected variables, which are thought to affect the results on physical objects, chemical formulation, structures, so forth. So the objective of a designed experiment is to determine which experimental factors influence the process output and to what degree. But before we start, I want to talk about avoiding the most common and fatal mistake, and that is not engaging the right people before you even start. You must start with consulting those most familiar with the process being investigated, the team that's closest to the process, and you do that by going to the Gemba, going to the production floor. If you're not comfortable with that, you need to bring in perhaps a facilitator, who's often used to organize the team to summarize their thoughts about those process factors and the settings that they think will make a difference in the product. So designed experiments are not a random process to be done on your own, a confidential or secretive effort completed in the office, performed in a hurry, or again, without the engagement of production, operations, quality, materials, engineering, and leadership. Don't even think about starting this process of experimenting and improving your process without these people engaged. So how about an example? As Jennifer mentioned, I worked in the automotive industry for 30 years, so this is kind of an automotive example. Suppose we are interested in studying the effects of proposed process changes for a machine that cuts stainless steel tubing to length. So underneath your cars or exhaust system, and those tubes are that exhaust, except if you're driving an electric car, exhaust fumes from your engine. That tubing is stainless steel, and that's what we're talking about. So the characteristic we're interested in is the length control. So here's on the right-hand side, kind of a pictorial of a cutting machine. What you see in the back are feed rolls, these orange things that contact the tube. You see this large tube being pushed through a series of clamp dies and this guillotine thing in the front that cuts the tube once the sensor tells it to sever the tube. So we meet with the tube cutting team, operators, maintenance, quality supervisors, etc. And they all agree that the quality, that is the length variation of our tube cutting, is determined by 4 process variables. The feed roll compound, the hardness or softness of the rolls, the feed speed, how quickly these rolls spin and feed the tube forward, the roll pressure, how hard the rolls are pushed onto the surface of the tube, and die clamp pressure, the clamping pressure on the tube. So we want to improve the quality of tube cut length, and our team has recommended that we test new process settings variables against the current settings. So experimental values, factor levels, and response variables are what we're talking about here. So our factors are feed roll compound, feed speed, roll pressure, and die clamp pressure, as we mentioned, and we're going to change from the present hard, fast, low, and low to the new levels of soft, slow, high, and high. Well, since our tubing cut lengths for this experiment are measured against a target, we'll set up a length gauge which indicates the target length is 0, and all lengths will show as plus or minus of that value. You have a digital indicator, they'll probably put in some kind of a length fixture. And suppose for the moment we start our experiment with a perfect process with a set of 16 measurements that are all zeros. So you see the 16 measurements in our little matrix on the left with factors A, B, C, and D in the current setting and the soft setting. So we start. So the first thing we'll do is we're going to change the feed roll compound from hard to soft. And when we do that, we see that the material change from hard to soft increases length by 2 millimeters. Factor A goes from A1 to A2. Next, we'll go to factor 2, feed speed, and feed speed decreases the length by 6 millimeters. So now A1, A2, now we have a B1, B2. You see that we drop that by 6. Next, we'll go to roll pressure. Well, roll pressure increases length by 4 millimeters. And finally, die clamp pressure. And die clamp pressure from low to high decreases by 2 millimeters. So we have A, B, 1 and 2, B, C, and D. So the question is, now that we have our results, our experiment is complete. The question is there a recognizable pattern in the data? And there isn't. That's the problem. That's me over here on the right, trying to figure out what's going wrong. Starting with a set of numbers that were all identical, we layered the effects, that is responses, of 4 variables, factors, on a process to arrive at apparently a random set of values with no apparent pattern. Lots of effort with no good result. Well, in statistical problem solving, we work in the opposite direction. We start with a random condition and try to get back to the initial condition in the process. So a design experiment is a technique that reverses the process that produced the variation for example, in this table. By following a series of simple arithmetic steps, it's possible to separate the effects of the various factors and return to the original, separating the effects of the DOE. For example, we can separate the effects. I'm going to move my little box and see, if you just will, the average value at A1, take a look at the column 4, plus minus 20. The average level A2, 12 plus minus 12. So A2 minus A1, so the average effect there is 2. So the average effect of changing roll material from hard to soft was 2 millimeters. But before we proceed, let's review some definitions and terms. Main effects is a term that describes a measure for the comparison of the responses of each version, that is level of a factor, averaged over all version levels of other factors in the experiment. As demonstrated in the tube cutting example, the effect, that is the treatment, of changing a roll material from hard to soft is 2 millimeters in length. This value is known as the main effect of variable A. The same technique could be used to show the effect of changing the tube cutting example in factors B, C, and D. Experimental error is the variation in responses caused by extraneous variables other than those due to factors and blocks, which we'll define in a minute, which will add a degree of uncertainty to the observed response value. So when experiments are repeated, results vary from trial to trial, of course, even though the experimental materials, environmental conditions, and experiments are carefully controlled. Therefore, the occurrence of experimental error is inevitable in practical experimentation. Error in real life, there are rarely perfect processes that start with zero variation. A certain amount of variation is present in the process before we change the settings of the factors. This variation present in the data after we remove the effects is called residual variation. Residual variation is also referred to as experimental error. In most experiments, the importance of main effects and interactions are judged against this residual or inherent error variation. You'll see that when we get to our ANOVA tables. Residual variation can be viewed as the amount of variation in our processes if no changes were introduced. Replications are the set of all treatment combinations to be compared in an experiment. Each repetition is called a replicate. Since experimental error is almost invariably present, replication is required to increase the precision of the estimates of the effects. In order to do this effectively, all elements contributing to the experimental error should be included in the replication process. For some experiments, replication may be limited to repetition under essentially the same conditions, such as same facility or location or a short time interval or common batches of materials. This kind of replication is known as blocking. A block is a subdivision of the experiment space into a group of relatively homogeneous experimental units, between which the experimental error can be expected to be smaller than would be expected should a similar number of units be randomly located within that space. So the term block originated in agricultural experiments in which a field was subdivided into sections having common conditions such as exposure to wind, proximity of underground water, or depth of topsoil. In manufacturing situations, blocks are based, for example, on batches of raw material, production of a single operator, or the number of units in a day. What we're trying here is to reduce the amount of extraneous variation. So here's a term that gets a lot of people confused, and that is interactions. In addition to the main effects, another kind of effect is sometimes present in an experiment. This effect is called an interaction. An interaction is a term describing a measure for the differential comparison of the responses for each version of a factor at each of several versions of another factor. A two-level interaction is called an A-B interaction, for instance, and of course a three-level might be an A, B, and C. Let's take a look at the graph to the right. So this is an example of main effects plot for enjoyment of food and condiments. So in the first thing you see there, the first quadrant, you see hot dogs and ice cream, both very enjoyable, have a relatively high level of enjoyment. And condiments, chocolate sauce, really, really high, like 80, and mustard, about 75. However, when you might combine them, for example, if you take a look at the graph of mustard, which is the dotted line, mustard on a hot dog has relatively high enjoyment factor, but when you put mustard on ice cream, not so much. So what you see there is an interactive effect of mustard, and chocolate sauce on hot dogs and ice cream interactions. Let's look at a few DOE examples. So if you don't have this book, I'd urge you to go out there and buy it. It's a great text that I've looked at for many years. And that's Duncan's Quality Control and Industrial Statistics. And he introduces a one-way analysis of variance by doing this exercise that we'll go through, determining the melting point of hydroquinine in degrees centigrade. So he's interested in determining if these four thermometers are reading the same or there's some significant error there. So that's the question. Do the thermometers read differently, or is the variation due to chance error? So the first thing he does, because these computations sometimes are just numerically, they are arithmetic are just a little bit hard to deal with, he simply subtracts 172 from each just to simplify the calculations. Now that we have Microsoft Excel and others, this doesn't become a big problem. But we'll go with his example. So we have the four thermometers, and now we have a row here called column sums. 4.5 is the sum of the items here in column A, and 2.0 in B, and so forth. So we're going to be talking about some terms here: column sum of squares, total sum of squares, error sum of squares, and we won't go through these calculations because Duncan has provided some shortcuts for us to use. So before we go on, we need to talk about something called the F distribution. And ANOVAs are a test of hypothesis which utilize this test statistic called the F distribution. And what we're really trying to find out is, are things the same as in these pictures of the cute babies? And we're trying to determine if the null hypothesis is true, and that is that the various experimental trials do not change the process. Formulaically, it's mu of A equals the mu of B, mu of C, mu of D equals the mu of original for factors A, B, and C, and D. So in all your experiments, you're going to be setting a null hypothesis and an alternate hypothesis. So using the F distribution, if two or more estimates are made from your experiments, and the process variants are made from the group data, and these estimates are made in the ratios by dividing one into the other. And if both estimates come from the same normal distribution, this ratio forms a known distribution. It's called the F distribution. So the F distribution didn't come out of thin air. It was named after Ronald Fisher and George Seneca. It's a continuous probability distribution that arises frequently as the null distribution of the test statistic, most notably in the analysis of variance, Ronald Fisher, based in England, and George Seneca, I think, from the University of Wisconsin. Back to our experiment. So if we take our table here, and step one that Duncan provides us, these shortcut steps, is the square of the column sums. So 4.5 squared plus 2 squared plus minus 5 squared and 1 squared divided by 3. That it becomes 8.5. If you take the individuals and square them, 2 squared, 1 squared, 1.5 squared, so forth. And step 3, square the sum of individuals divided by the individuals. So all the individuals squared divided by 12 individuals. That becomes something called the correction factor. In our experiment, we're going to be using 5% risk value. So the column sum of squares is 8.5, you see that on the left, minus the correction factor, 4.42. Total sum of squares is 15 minus the correction factor equals 10.92. And the total sum of squares is, the error sum of squares is total minus column. So it's 10.92 minus 4.42 equals 6.5. So we're going to be using the F table, and I just wanted to show this one I pulled off the internet. We're going to be looking at, again, the ratio of variances, the degrees in the numerator and across the vertical degrees in the denominator. And we're going to be looking for 3 and 8. I'll show you that in a minute. And our critical factor for making this decision, whether these thermometers exceed the critical value, and the critical value for 5%, the alpha 5% is 4.07. Now we have Excel, and you can plug these numbers into Excel, and it gives you this table where, again, for alpha 5%, we have our degrees of freedom. That's 3, 4 thermometers, 3 degrees of freedom. And we have 12 individuals, so our total is 11 degrees of freedom. That means by addition, or I guess subtraction, our within group is 8, so 3 plus 8 is 11. So the mean square is the sum of squares divided by the degrees of freedom. So 4.417 divided by 3 is 1.472, and our F is the ratio of the mean squared of between groups to the mean square of within groups, and that F, therefore, that ratio is 1.812. Remember, our critical value is 4.07. So our F for this experiment, 1.812, does not exceed the critical value. So that means that we accept the null hypothesis, the innocent hypothesis that says all the thermometers are the same. That's good news. So Duncan also shows us quite simply how to take the next step, and that is to compare the thermometers and perhaps analysts, as he does here. In this case, we're going to be using the same table, but we're going to be using different sources of variation. So the columns, again, 3 degrees of freedom. Rows, analysts, 2 degrees of freedom. Our experimental error will be 6, again, because the total is 11. So in our F table, we'll be looking at 3 and 6 and 2 and 6. So our critical F factors, 4.76 and 5.17. And this time I used a piece of software called QI, which I'll be introducing in a minute. And this shows us, again, the columns, thermometers for the V1 versus V2 at 5% error, critical factor 4.76. Again, we see F of 3.79. So we accept the null hypothesis because 3.79 is less than 4.6. However, the critical factor for F, here is the F factor of the rows, that is the analyst, 5.37, exceeds the 5.14. So therefore, we do have a difference. We can't accept the null hypothesis for the analyst. So we accept the null hypothesis that the thermometer is the same, but we reject the null hypothesis that the analysts are the same. We have to go and work on why the analysts are reading thermometers differently. One-way and two-way analysis of variance. I know I went through that pretty quickly. If you have any questions, I'm sure we can address some later on. So the next thing I'd like to talk about is full factorial and fractional factorials. And of the fractional factorials, I'll be talking about the Taguchi method. So a full factorial experiment is an experiment whose design consists of 2 or more factors, each with discrete possible values or levels, and whose experimental units take on all possible combinations of these levels across such factors. While a fractional factorial design is one whose design consists of a carefully chosen subset of those experimental runs of fractional factorials. So a little picture here, a full factorial, we would run 7 factors at 2 levels. We'd have to run 128 trials, while a fractional factorial of 7 factors at 2 levels, only 8 trials. So you can see the advantage of running a fractional factorial over a full factorial. Here's a little table that says the same thing. So there are 7 factors at 2 levels, 128, and if you replicate them, you're talking about 256 trials. And believe me, if you're running 256 trials, you'll have nothing but a mess because you'll never be able to duplicate all those conditions all the time. Nevertheless, here's an example of a full factorial. So your team has determined that pressure, temperature, and chemical concentrations are the three key variables affecting the yield of a chemical process, which is currently running at only 64%. So temperature in yellow, pressure in green, and concentration level in blue. And you notice the matrix that is provided is, for example, under temperature, it's low, high, low, high, low, high. And pressure, it's low, low, high, high, low, low, high, high. And in concentration, it's 4 lows and 4 highs. We see the responses. Again, this matrix is a full factorial matrix. When we get to fractional factorial, the matrices are quite different. So here's the results, again, using QI macros and our factors as we reflected them in the previous slide. And here's a table of contrast. If you take those results and go across the highs and lows, you may want to stop your experiment right here and not go to your F table. You can see that the temperature contrast between low and high is a difference between 52.25 and 75.75. It's a huge contrast. And that's reflected in the graph that you see at the right. You see that temperature has a huge contrast compared to the pressure contrast and the concentration contrast. So you may want to stop the experiment and say, holy cow, let's talk about temperature, because that's really the big dog in this fight. But in this case, we'll go ahead and do the analysis. That we can see that the temperature F is 245. It's enormous. That's a full factorial, and this QI software also provides us with the tables here, and that's quite helpful if you want to look at it graphically. Because full factorial designs can get extremely cumbersome, as a manner of speaking, as the number of factors go up, experimenters have searched for an alternate technique to improve the efficiency of their tests. And one of the techniques that solve this problem is called a fractional factorial design. Again, developed by Sir Ronald Fisher back in, he lived between 1890 and 1962. Now, although fractional factorial experiments have been around for a long, long time, they've only become recently more popular, and the popularity of this type of experiment is primarily based on the work of a Japanese engineer, and the technique is often referred to as the Taguchi method. That's Genichi Taguchi there to the right, even though clearly he didn't invent it. The Taguchi method was conceived by Dr. Genichi Taguchi while he's working for the Japanese Electrical Communication Laboratory following World War II. Taguchi's purpose was to improve the efficiency of research and development experimentation. Taguchi methods were widely trained in the United States by a company called the American Supplier Institute and the Ford Motor Company during the mid-'80s. And I was a quality engineer at that time, and the company sent me to see Dr. Taguchi's work, and I was fortunate to be able to participate in Shin Taguchi's and the American Supplier Institute's training on the Taguchi designed experiment. Quite lucky to be in that opportunity to do that. Taguchi and his team developed a series of orthogonal arrays which systematically partitioned experimental variation into structured patterns. In addition, they developed a series of linear graphs that allow experimenter to organize and experiment for reduced time and expense. That's a big, big deal. But most importantly, Taguchi developed a new philosophy of DOE, and that is that DOE is an engineering tool to enhance productivity, not a mathematical model. And cost effectiveness and efficiency are more important to the engineer than mathematical rigor, which is why some classical statisticians have a little bit of friction with the Taguchi methods, because it's more of an engineering tool. Product development and reliability improvement and process improvement are opportunities for continual and incremental change. It's not a one and done process. The idea is to continue to do these design experiments, fine tuning and honing the process. So it's not just once they do it and complete. What you see on the right is one of the Taguchi experimental matrices, these orthogonal arrays. It's called a L8 because there are 8 trials there on the left. Across the top, 7 factors. Excuse me. Orthogonal arrays specify how many factors we can use, how many trials to run, and where to set each factor for each trial, and also gives us hints to make it more economical. The simplest array that I've used is the L4, and that's 4 trials on 3 factors. So again, the L8 is 8 trials or experimentals or setups are performed. And you can see the matrix is different than that full factorial, where in trial 1, it's 1 change between factor 1 and 2. In addition to that, Taguchi introduced these linear graphs, and these are provided. So when assigning factors to the orthogonal arrays, if we wish to track potential interactions, if the group thinks they are important, we use these linear graphs. Linear graphs are visual aids to help in assigning the experimental variables. For the L8, there are 2 types of linear graphs, one that we look sort of like a fishbone there, another one like like a triangle. However, if only 4 factors are needed, you'd assign them to column 1 sort of at the top of the triangle, column 4, column 2, column 7. However, if you were interested in interactions, then you'd say, well, interaction between A and C would fall into column 5. A BC interaction would fall in column 6 between 2 and 4. And an AB interaction would fall in column 3 between 2 and 1. So although Taguchi's fractional factorial experiments come in all sizes and shapes, the basic method is the same for any design. And the experiment can be simplified to a few basic steps that apply to any design. First is to plan the experiment. And again, with the people involved, with the people who know most about the process. Then you select an orthogonal array that best fits the plan. Select a linear graph that allows the best assignment of the factors to the orthogonal array, and then assign the factors to the column in the orthogonal array. Run the experiment, analyze the experiment, and draw appropriate conclusions from the analysis. Determine which factors at which levels really drive the process, and then verify the result by performing a confirming run. I've used QI macros, not a sponsor, of course, but I'd recommend the software. It works very well for me. So congratulations on making it through this introduction to design experiments. I know I went through it pretty fast. There's lots of good references available in texts and in classrooms or online. Don't be intimidated by the terminology. It's not as bad or severe as it seems. I'd like to thank the Statistics Division for the opportunity to present today. Steve Shkula and Jennifer Hollering, thank you very much for the opportunity. Some credits and references to the American Society for Quality Control, the Greater Detroit section that introduced me to hypothesis testing and design experiments. Ford Motor Company and their work with the American Supplier Institute and Genichi Taguchi and Yuan Wu's offline quality control. Book I mentioned before, Quality Control and Industrial Statistics by Duncan. Glossary and Tables for Statistical Quality Control. That's published by the ASQC Statistics Division's QI Macro Software. Statistic by Jim, which showed me that great example of interactions. Wikipedia, and my friend, Mr. Tom Dole, who worked with me to develop this information many years ago. Again, thanks to the Statistics Division and Steve and Jennifer. That's it, Jennifer.
Thanks, Mike. That was great. Any questions from anyone out in the audience? You can put them in the chat. I know it's getting late. We have a couple minutes if anybody has a couple minutes to stay for a question or two.
Should I stop sharing?
You can leave it on this page if you want. That's fine.
Okay.
We'll just give people a minute or so if there's any questions on the chat. Okay, here's a question, Mike. when I propose design of experiments, usually I get pushback from the engineers on the binary levels of the factors as opposed to a range. Have you encountered this? If so, how do you deal with it?
Well, it's a good question. Thank you very much. When you set up the experiment, what you want to do is ask the engineers, which is the range that the widest range that you would anticipate or think that the process should run at, and and take those two high and low levels, and you don't want to choose two levels of a factor that are very close to each other, because you want to be able to tell if that factor makes a difference. So select the range to be as wide without making scrap. Okay, select that range to be as wide as possible. Now, if they think that it's some kind of a curve, maybe you can go with some of the matrices that are 3-level and range. If you think that the distribution is some kind of exponential or geometric shape.
I know sometimes I have the same issue where they want the operators to have the ability to make adjustments, and so they don't like to make them stay at just one spot. So it takes some convincing. Have you run into that?
Well, I mean, yes, everybody likes to turn the knobs because they see variation in the output and they want to make it better. What we have to talk to people about is variation of the product is normal if it's in control. So what you want to do is leave the process alone until you found out that the process is out of control or out of spec. And you do that by using statistical process control. You certainly don't fool around with the process unless you know that the process has changed, either through points beyond the control limits, 7 points in a row that either ascend or descends or shifts in the process. So, you want to discourage people from fooling around with the process until they have a statistical signal that says that they should. And if not, then you're really losing control.
Here's another question. What are the barriers you see when trying to use design of experiments in industry, just in general?
Well, they're not cheap to do. Oftentimes, it's it takes time to set up production, do the changeovers, and so that's the whole point of using fractional factorial experiments. You can test as many as 7 variables in 8 trials. I made the mistake early in my career of using design experiments. We had an enormous experimental design with I can't remember, it was 32 different variables, I think it was. And the problem is it just took so long to run the trial. And because it took multiple days, multiple operators, multiple lots of material, we sort of introduced more variation than we should have. So what you'd like to do is make it a very simple design. If you can get it down to an L4, I mean, that's only 4 trials. You're using maybe three variables. I mean, you say, well, maybe there's more variables. Well, let's see, of the 3 variables, which one are they all very, very important, or can we prove that 1 or 2 of the other are not important? So start with a very, very small trial. They're cheaper and quicker to do. And believe me, once you can show that you know what you're doing, and once you can show success and publicize the success, people will start believing in what you can do, and then you'll have a better time of it.
Great. I don't see any other questions, so thanks, Michael. That was a very, very great topic today. Very informative, and we're gonna end the webinar for today. I appreciate everybody's attendance. Thank you.
Thank you all.